as weights, infinite weights. So the center of gravity of the body is the point of application of these resultant forces. Say for this object, it may be like some this point. All these forces will be acting or concentrated. So this point is called as the center of gravity of the body, where the all weight of the object is concentrated. This is for a case of a body. Coming to the planar shapes, like a geometrical figure, as you see here, a triangle one, the term center of gravity is not appropriate as it is not having any weight. The term to introduce or to designate the center of this geometrical shape is called as a centroid, which is the possible or probable center of the geometric figure. So a geometric figure does not possess the weight, and hence the term center of gravity cannot be applied to this geometrical area. We use the term centroid for the planar surfaces. That's the difference between center of gravity for an object and the centroid for a planar figure. So we are focusing in this module on the centroid of an area. So the planar areas. You can see a planar area here, a irregular one, uh, which is placed with respect to the axis x and y. So we are focusing on the centroid of the area, and the centroid of an area is the geometric center of area where entire area can be assumed to be concentrated. So we are assuming the entire area is concentrated at the point G here. So the G point is actually at a distance of x bar from the y axis. So we have the vertical y and we have the horizontal x. So it is by x bar from the y axis, and it is a distance of y bar from the x axis. So it is explained here. And the centroidal axis means it is the axis through which the centroid passes. So you can this is an imaginary axis which is like this. Yeah. The next terminology is the axis of symmetry. So the you can see here two figures, geometrical figures. One is an isosceles triangle and one is a rectangle. So we are supposed to find the centroid of this planar figure. So centroid means for a planar figure there will be two components, like the previous slide. One is x bar, distance from the vertical axis, and the y bar from the horizontal axis. So when you consider this isosceles triangle figure, you can see that this is having an axis of symmetry with respect to the vertical. So that means that our y bar, our y bar will be in the line of the axis, and the x bar have to be found out because it is not symmetrical in both the directions. So we have as we have one axis of symmetry, one of the centroidal coordinate will pass through that like the symmetrical axis. Coming to the case of a rectangle, where we have the breadth and length, this is actually symmetrical about both the vertical as well as the horizontal axis. So that means the line passing through the centroids or the line of symmetry will be the centroidal axis. Coming to the definition, the centroid of an area lies on the axis of symmetry if it exists. So we have here, when there are two axes of symmetry, the point of intersection of the axis of symmetry will be the centroid of the area. Right. So നിങ്ങൾക്ക് ഇത് ഒന്ന് വിഷ്വലൈസ് ചെയ്യാനായിട്ട് ഇപ്പം നിങ്ങൾ ചിലവരൊക്കെ തന്നെ നിങ്ങൾ നോട്ട്ബുക്ക് ഒരു വിരലിനെ കറക്കുന്നുണ്ടാവും. അപ്പോൾ അതിനെ കറക്കുമ്പോഴും നമ്മുടെ വിരൽ ആ കറക്റ്റായിട്ട് സെൻറ്ററിൽ വരുമ്പോഴാണ് ആ റൊട്ടേഷനും പ്രോപ്പർ ആവുള്ളൂ. അത് കുറച്ചും കൂടി ഡിഫറെൻ്റ് ആണ്, കാര്യം അതൊരു റൊട്ടേഷണൽ എഫക്റ്റ് വരുന്നുണ്ട്. ബട്ട് യു ക്യാൻ തിങ്ക് ഇൻ ദാറ്റ് വേ. സോ ഇറ്റ് ഈസ് ദ പോയിന്റ് വേർ ദ എൻറ്റയർ ഏരിയ ഈസ് കോൺസെൻട്രേറ്റഡ്. Now we have the expressions for x and y. So we are dealing with an irregular shape. You can see here an irregular shape which doesn't have any axis of symmetry. So we are going to fix the centroid, right? For a planar figure, we are assuming it as a g with respect to the given axis x and the y. So consider an area. So area is our full area of this irregular shape, and we are dividing this total area into numerous small areas like a1, a2, a3, etc. are there, and we are considering the x1, x2, x3 are the individual centroid distances. So say for this area a1, it is actually at a distance of x1 from the y-axis and y1 from the x-axis. Similarly a2, x2 and y2. So we have numerous areas. So x1, x2 are the distance from the vertical axis, and the y1, y2, y3 are from the x-axis. Now we are taking the sum of moments of this elemental area about the y-axis. So it is like the A1 area into lever arm. So area into lever arm is x1 plus A2 into x2 plus A3 into x3. It goes on. Since the entire area A is assumed, so we are fixing or we are assuming that the entire area is actually concentrating at a point G. This addition can be equated to total area into the total centroid, like a into capital A into x bar. So we are equating this addition with the total value. So a into total area into x bar is equal to a1 plus a2 plus a3 all into x. So equating the sum of moments of the elemental area about the y-axis and the moment of entire area about the y-axis. So we are equating both these, like a1 into x1 plus a2 into x2 all is equal to, so we are splitting the total a will be the combination of a1 plus a2 plus a3, so all into x bar. So by equating this we can get the value of the x bar, which is the required parameter. So next slide, x bar is equal to what, a1 x1 plus a2 x2 all this on the left side divided by the area, total area, will give you the x bar value. So it is actually sigma a into x by sigma a. In another form it is integral over integral ax by integral a. So x bar is equal to x integral x into dA by integral dA. So the same can be repeated with respect to the x-axis to find the y bar. Same derivation, but the x will be replaced by the y times. So we will ultimately reach at y bar is equal to integral y into dA by divided by integral dA. So this is an important formula by which we are going to solve for different geometrical shapes. So this problem will make this concept clear. We have a rectangle here, right? So we know that being the figure symmetrical about both the axes, the centroid will pass through the exact symmetry. So we can have a guess that the centroid will be at a distance of b by 2 from the y-axis and at a distance of d by 2, d is the depth, from the x-axis. So we are going to prove that now. Consider a horizontal strip of thickness dy. We can see here a dy strip here from the x-axis as shown in the figure. Elemental area dA, we are considering this differentiated portion. dA is equal to b into dy. Depth is dy and total breadth is b. So we have this equation. To find the y bar, we have the equation y bar is equal to integral over y into dA by integral dA. So the y actually ranges from 0 to d, the depth 0 to d, y into dA. So dA can be replaced by the b into dy. So we have the equations b into dy replacing, then integrating the y. So b and dy are the, b is a constant and dy is a integrand required. So b into, taking out b into y is y square by 2 integrating over d divided by b into y. Upon simplifying, we will actually yeah, this y will get cancelled and we'll get d by 2, which is our assumption that the y bar will be the d by 2, being symmetrical. Y bar is d by 2. We are getting the same from the derivation. The similar steps for the x bar. Only thing is that we have to consider different strip of width dx at a distance of x from the y. So doing the repeated steps similar to the previous one, we will get that the x bar is equal to b by 2. So we get the centroidal axis which is passing through the axis of symmetry in the case of rectangle. So this is actually the centroidal axis which is passing through the center of through the axis of symmetry. So the small difference between the center of gravity and centroid, we have seen that it is for an object, is for a planar area. So center of gravity applies to bodies with masses and weight, whereas the centroid applies to only the plane areas. It is for center of gravity, it is a point through which the resultant gravitational force weight act for any orientation of the body. For the case of centroid, it is a point in a plane area such that the moment of area through any axis through that point will be equal to 0. So you can study this for exam purpose, the difference between center of gravity and centroid. Coming to the new problem, we have to find the centroid for a right angle triangle. Yeah, tell me. Coming back to the slides. So for this triangular figure, geometrical figure, actually there is no axis of symmetry, right? We can't find any axis of symmetry. Even on vertical also, it is not in symmetry. Even horizontal also not in symmetry. So we can guess the centroid properly. So we can use the equations to find the centroid. The same equations which we have used before. Yeah, coming to this problem. So we have consider an elemental strip of width b1. We have the width b1 here, and the thickness dy at a distance of from the x-axis. So we are having the x here horizontal, y vertical. This is a strip which we need to find the y bar, and the dA is equal to b1. B is the total width. We are assuming that this width is actually the b1, and dy is the depth of the strip. So dA is equal to b1 into dy. So we have the total height uh, as h, and actually we have to find the b1 by the similar triangles. So the b1 by b is equal to h minus y. So this width by total width is equal to this height, which is total is h, this is y. So h minus y is this value uh, divided by total height. We can find the b1 as b by h into h minus y. So the dA was b1 into dy. So the same b1 we have into dy. Then you can use the equation y bar is equal to integral y into dA by integral dA. We can substitute the values here. So integral y into dA, y into this term will be the dA term divided by b by h into h minus y. So this h will get cancelled. So we have yeah, b also will get cancelled. So this y into h will be coming in the numerator, h into y minus y square divided by this b and h will cancel with respect to the numerator. So h minus y will be the denominator. Then you are integrating it over the h, which is the vertical value. So you can do the integration and you will find that after simplification you will end up at the value of y bar is equal to h by 3. So this means that for a triangular figure, the centroid y bar, so that means from the x-axis the centroid is at the distance of h by 3. So preferably at maybe at this point will be the y bar value. Now we have to find the x bar with respect to the vertical axis. So we have to take the integration over x into dA by integral dA. So I'm not repeating the steps. The same steps will follow, except that the strip has to be taken now, which is parallel to the y-axis. So dA is equal to h1 into dx. So you can apply the similar triangles formula to find the dA as before. And after solving all these integrands, we will find that the x bar is equal to b by 3. So note the similarity that the y bar is h by 3, one third of the height, and the x bar is b by 3, one third of the breadth. So preferably the x bar y bar, the coordinate axis centroid will be at this you can see the cursor here at this point, which is a distance of b by 3 from the vertical axis and h by 3 from the horizontal axis. So this actually this value is constant. That means you can directly use this formula for finding the centroid of the maybe a right angle for a right angle triangle, and the for rectangle you can use directly the d by 2 and the b by 2. So yeah, so this is actually an application for finding the centroid. So you have a figure like this, a geometrical figure like this, and we are supposed to find the centroid of this shaded portion alone. So to find the centroid portion of this shaded portion, you can either you can do it directly, as you know directly the uh, centroid of this triangle. For demo purpose, here it is shown that we are actually deducting the this non-shaded portion from the total rectangle. That means that you can see here. No, sorry, actually it is directly given. How to find that? I will just tell you. X bar is equal to b minus 1 by 3 into b. So you can see you are supposed to find the centroid of this shaded region. So we know that for a triangle, the x bar as well as the y bar is with respect to this 90-degree angle, or this right angled portion. From this portion only we are measuring b by 3 as well as the h by 3. So this is actually an inverted triangle, right? So we are actually focusing to find the centroid with respect to the O. In that case, x bar is equal to b minus one third of b. So for this, yeah, for this triangle, we have the total width is b, and one third of b will be from this point up to this point. So deducting this centroid, you will get the centroid of the triangle lamina. So I made a little confusion. Actually, the b x bar. So we are finding b bar. B bar is a total one minus one third of b. Yeah, I'm coming to that again. So here you see that we have to find the centroid with respect to this axis, x and y axis. So you know the centroid with respect to this point as b by 3 and h by 3. So with respect to this axis, this like y o x, you have to find the x bar. S bar is equal to b minus one third of b, because one third of b is from here to here. So from, okay, that means that, see this one third of b is there, no, one third of b, one third of b is from this point to this point, say this point. So we are supposed to find the x bar from here to this point. So total b minus one third of b by one third of b will give you two third of b, which is this distance from the left extreme to the centroid of this lamina. Similarly, y bar. So y bar means, you know that the y bar is at a distance of h by 3. We have h as the height, h by 3 from the base. This is the base, right? So you have to find from this point. So may from this point to this point. Yeah. That means that total we have h minus one third of h. One third of h will be this like circled portion. So we'll get the y bar with respect to this point, this horizontal x-axis. So the main takeaway from this simple solution is that the centroid depends with respect to the coordinate axis chosen, right? That is, we have chosen the xy coordinate as the coordinate with respect to we have to define the centroid. So that's why this these types of changes are there in the calculation. Okay, so we will jump to the next problem, which is the centroid of an isosceles triangle. You know that the isosceles triangle, for isosceles triangle there is an axis of symmetry, which is this. This is the axis of symmetry, right? So yeah, and so as this is the axis of symmetry with respect to the xy coordinate, so this is actually s, this is actually y, and being the axis of symmetry directly, the x bar centroid will be the b by 2. B is the total width of this isosceles triangle, so b by 2 will be the x bar distance, and y bar is equal to one third of h. It is the centroid of the triangle. So these two triangles are side by side, right? So you can so for both the left side as well as right side, the centroid will be at the same point, one third of h. So for this symmetrical arrangement also, centroid will be the one third of h. And for the case of centroid of a circle, so circle being a symmetrical shape in all the direction, that means both direction. So we have the x bar and y bar is equal to d by 2. So at the proper centroid of a circle, uh, we have the value as x bar y bar is equal to d by 2 when the circle is very close to the coordinates. Yeah. So next derivation is to find the centroid of a quarter circle. So you have a quarter circle here, which is having an axis for radius of r, capital R, and it is given the x-axis as well as the y-axis is actually passing through the section. It is not actually with respect to the origin. It is the axis is at the center portion, and it is noted that the x is measured from the vertical axis, and y is also y also has to be accounted. Okay, so consider a quarter of a circular area. Consider a quarter of a circular area as shown in the figure of radius r. Consider an element a distance of r from the center. So we have the center here. So actually, you ignore this exercises. This is actually only an indication of the x and y axis coordinates. So we are considering the all the derivation with respect to this centroid. So this is only for the reference x and y. As that's why it's shown in the dotted lines. It is not the real axis. We are taking with respect to this centroidal axis. Okay, coming back. Consider an element a distance of r from the center O. So we are taking the an area like this, which is a distance of small r from the centroid, and the radial width. So the radial width is given as dr, and it is bound by the radius. So for this sector, for this small portion, two boundaries are there, line 1 and line 2. The line 1 is theta angle with respect to the horizontal. So one boundary theta, and the second boundary is theta plus d theta. So this line is actually theta plus d theta with respect to the horizontal. The area of the element dA is equal to r into d theta. So r into d theta will give you this value, this arc length, right? So this arc length into this thickness into dr will give you the selected or considered area of the element. And we have the notations like the y x is equal to r cos theta. So we are taking x here, and y is this one. So x is equal to r cos theta, cos component of this triangle, so r cos theta, and y is equal to r sin theta. And so x bar, we know the equation is equal to integral over x into dA by integral dA. So we are integrating, doing double integral 0 to pi by 2. So the full right angled, and also in the radial direction, integral over 0 to pi by 2, 0 to r. The dA we got from the previous slide, that is dA is equal to r into d theta into dr. So r into d theta into dr. So dA is equal to r into so we also know that x is equal to r cos theta, right? So and y is equal to r sin theta. So all those terms are added here. We are replacing the x with the r cos theta, and this r into d theta into dr will be the dA component, divided by the dA component is r into dr into d theta. So this is the integrand, and we can, you know, the integration, and upon simplification you will get that the x bar is equal to 4r by 3 pi. That is centroid of this like area is at a distance of 4r by 3 pi from the vertical axis. X bar is measured from the vertical y axis, and y bar from the horizontal x axis, right? So 4r by 3 pi is the x bar, and y bar is given by you can follow the same like you can use same figure. Only thing is that the y bar is equal to the x has to be replaced by the y. So this r cos theta is changing to r sin theta. That's all same, and you can perform the integration, and you will end up with the same value 4r by 3 pi for the y bar. So for a sector, you have the y bar and x bar is equal to 4r by 3 pi. This is an different case. You are asked to find the centroid of this shaded portion with respect to the horizontal axis. So our axis is like this. This is our axis. I'll show that. Yeah, our axis is sorry for this. Yeah. So this is our axis, but this is vertical and this is horizontal. So to find that, we know that the 4r by 3 pi y bar as well as the x bar is from this point. If you check back the derivation, the both yeah, we are taking the 4r by 3 pi and as x bar as well as the y bar from this origin point, right? So coming to this question or this part, the 4r by 3 pi is from this point, from here to here, and the y bar is also from here to here. So the real x bar, or for this question, x bar is has to measure from this line, this left line, left vertical line, is equal to r is the total radius, r minus 4r by 3 pi. So from this point to this point, x bar is equal to r minus 4r by 3 pi. Similarly, y bar is equal to r minus 4r by 3 pi, because 4r by 3 pi y bar is from this point to this point. So should measure for this coordinate system from here to here, which is total radius minus this value is from here to here is the r minus 4r by 3 pi. And this is a direct equation that centroid of a sector of a circle, uh, being this is yeah, this is a sector of a circle, and for this one, it is symmetrical area with respect to the horizontal. And for this one, we have x bar is equal to 4r into sine alpha by 2 by 3 alpha as the direct equation for the centroid of sector of a circle. So I think I will stop for today.